So in this lecture, we have this continuous beam, and we are going to analyze this continuous beam using finite element method, right? So here you can see we have a end. If you will see the end, because first step, what is our first step? First step is to identify the nodes. So here we will identify the nodes. So at the end, both the ends we have to give the nodes. So at A point there is a node, right? As well as at C also there is a node, because these two are the end. And as well as if you will see at the B, there is a support. Apart from this, from B, C, this AB span is unloaded, whereas your BC span is loaded. So here force is acting, load is acting. When we were discussing about this, how to select a node, I have said at the ends we have to select, then wherever there is sudden change in area, as well as when there ever is a load acting. So here from B point you can see there is a load acting, right? So at the B point also we have to select the node. So we have three nodes here. Let us take this is node number 1, let us take this is node number 2, and let us take this is node number 3. So we have three nodes. So as soon as we have three nodes, we understood that there is two element. This is your element number 1, element 1, and this will be your element number 2, element number 2. So we have two elements here. Element 1 is between node number 1 and 2, and element number 2 is between node number 2 and 3. So what we need to find here, we need to find the slope at second node and third node. Slope at second node and third node, what does it mean? It means we need to find the value of theta 2 and we need to find the value of theta 3. Okay. Apart from this, what they are asking, and find vertical deflection at the midpoint of the distributed load. So somewhere at this point, which is at the mid means from here to here the distance is 0.5 meter. Let us take this is 0.5 meter. So at this point, let us take this point as P point. At P point, what will be the vertical deflection? So that also we need to calculate. So how we will calculate? The approach is as usual, same, right? We will consider the displacement at each node. So what are the displacement at first node? That we will consider V1 theta 1. So here at node number 1, at node 1, our displacements are V1 and theta 1. Similarly for at node 2, we will have V2 theta 2, and at node 3, let us take the displacements are V3 theta 3. Now we will see the forces. These all are the displacements. So already we know in a beam element at a node there are two displacements, V1 and theta. V is the vertical displacement, theta is the slope. So now coming to the forces, so let us draw the free body diagram. Forces, you know, we will take shear force and bending moment diagram. Apart from this, we have a distributed load, so we will have the impact of this distributed load also. So we will take additional load also. What we will take, let us see. So let us draw the free body diagram now. This is fixed end, right? This is node number 1. Let us take this is node number 2, and here let us take this is node number 3. So at node number 1, we have forces. Let us take, we have forces F1. At node number 2, let us take the force is F2, and at node number 3, let us take the force is F3. These all are the shear forces. Now coming to bending moment, let us take at node 1, bending moment is M1. At node number 2, let us take bending moment is M2. At node number 3, let us take bending moment is M3. And we know the distance span is 1 meter. Now coming to additional forces, what are that? Those are additional forces. So let us see what are that additional forces. This additional forces will be due to the load. that is distributor load, here UDL 12 kilonewton per meter from second node to third node. So we did not to there is no need of taking the element 1 here, means from node 1 to node 2, because if you will see element 1, there is no node, right? There is no load in element number 1. So only we are going to consider element number 2. Element number 2 means in between node 2 and node number 3. So here we will have additional force. And what are those additional forces? Let us take that additional forces is F2D, and here that is F3D, right? And the moment is, let us take the moment is M2D, and here the moment is M3D. D means due to this distributed load, the additional force. Already we have considered this thing while deriving the stiffness matrix for the beam element. Already we have discussed all the things. Once we will proceed the problem, you will come to know what is this F2D, F3D, M2D and M3D. This is all due to this application of load here. This is the basic condition, right? The basic thing, if there is no load, we have this much forces, shear forces and bending moments. And this is due to the application of load. Now, let us consider a problem in which on this span also there is UDL. Suppose, for example, I am taking, there is a problem same like this only. On this span also there is UDL, and on this span also there is UDL. Let us take this is W kilonewton per meter, and let us take this is a small w kilonewton, means intensities are different. In both the cases, intensity, this is a small w kilonewton per meter, this is capital W kilonewton per meter. So in this case, what we will do, we have to take, this is node 1, this is node 2, this is node 3. Here also we need to take node number 2 because the intensity of load is changing, right? So once the intensity of load is changing, we have to consider node in this case also. So in this case, what will happen? Not for only element number 2, for element 1 also and element number 2 also, we have to take these things, the additional forces and additional moments. Like here, if it will be F1D, here it will be F2D. Similarly, here also it will be F2D, here it will be F3D, right? Because this is second node. So if you will divide it, it will be 1, 2, 2, 3. So here it is 1, 2, 2, 3. Similarly, we will have moments also. Similarly, we will have moments also. So here we will have M1D, M2D, then again here M2D, and then here M3D, right? So if the problem will have loading on both the spans, we will go for this. This is only the difference, otherwise remaining things is going to be same. So just try to understand in which case we are going to take the additional load, additional forces, where there is a loading. If there is no loading, we will not take the additional forces like F1D and M1D. So here there is no load in the element number 1, so no need to take here in this portion. So only we will take in between node number 2 and node number 3. So I have taken here, right? So let us remove this. I hope you understood why we have taken this additional forces. So now we have taken all the things. So what is our next step now? Our next step is to calculate the stiffness matrix, right? We will calculate the stiffness matrix now, stiffness matrix for element number 1, and then stiffness matrix for element number 2. Everything is given. A stiffness matrix is what? EI upon L cube into that big matrix 12 6L minus 12 6L, like this. So let us take the next slide now. We will calculate stiffness matrix for element number 1. That will be equal to E1 I1 upon L1 cube into the matrix is, we know the matrix 12, already we have derived the matrix, 6L minus 12, 6L, then we will have 6L, 4L square, then we will have minus 6L, then we will have 2L square, then we will have minus 12, then minus 6L, then we will have 12 minus 6L, and then 6L, 2L square, then we will have minus 6L and 4L square. This is the stiffness matrix, right? So here just we will put all these values of E, I and L, and here again we will put L values. So you can see here the L value is given as 1 meter, E value is given, and I value is given. That is constant for element 1 also and element 2 also. So EI by LQ is going to be same, right? And the inside, whatever the values are there inside also, that all depends upon L. So if you will see here, even the length span is also same. So whatever the matrix we are going to get, that will be valid for element 1 or element 2 also. Means we are going to get the identical matrix, right? No need to calculate again and again. K1 will be here equal to K2 because each and everything is same itself, right? There is no change in that specification. E value is same, I value is same, L value is same. So we are going to get K1 value and K2 value as same. So let us write the K1 and K2 value. After putting all these values of E, I and L, we will get K1 and K2 as, let us write K1 value. K1 value will be equal to 8 into 10 to the power 5 into 12, and L value is 1, so then it will be 6 into 1, it will be 6 only, right? So 6 minus 12, 6, then we will have 6 L square again 4, then minus 6, 2, then we will have minus 12, then minus 6, 12, minus 6, 6, 2, minus 6 and 4. Similarly, we will have K2 value also same. We will have same K2 value as K1 because everything is, every specification are same. So 12, 6, minus 2, 6, then again 6, 4, minus 6, 2, then minus 12, then minus 6, then again 12, sorry, this, let me write it as plus 12 itself, minus 6, then 6, 2, minus 6 and 4. So we have this K1 and K2 value. Once we have this K1 and K2 value, what we will write, because we need to find the global stiffness matrix, right? So for finding global stiffness matrix, we should know which row is belongs to which displacements, which column is belongs to which displacement, right? So for K1, K1 is between first node and second node. If you will see the problem, K1 will be for element 1, node 1 to node 2. So V1, we can write here, this will be V1, theta 1, V2, theta 2. Same, we will repeat it here also, V1, theta 1, V2, theta 2. Now for K2, it will be between 2 and 3. So V2, theta 2, V3, theta 3. Similarly, we will repeat it again, same, V3 and theta 3. Now we have K1 and K2 values, so we can find the global stiffness matrix. So global stiffness matrix will be, now we can write the global stiffness matrix. Global stiffness matrix, if you will write that global stiffness matrix, it is going to be for V1, theta 1, V2, theta 2, V3, theta 3. Similarly, here we will repeat it again, V1, theta 1, V2, theta 2, V3 and theta 3. Just we need to see K1, K2 and we have to put the elements here. Like V1 at this point, V1, V1. So V1, V1 will be in K1, right? That is 12. Already we have discussed this thing in the previous classes, how to find the global stiffness matrix. So same pattern, same thing we have to do here. Global V1, V1 is 12. So we'll write here 12. Similarly, theta 1 V1, what is theta 1 V1? See here, theta 1 V1, that value is 6. So we'll write here 6. Then V2 V1, V2 V1, V2 V1 minus 12. So we'll write here minus 12. Theta 2 V1, what is theta 2 V1? Theta 2 V1, 6. So we'll write here 6. V3 V1, there is no relation between V3 V1. You can see here, here it is V1, there is no V3. Here there is no V1 term, right? With respect to V3. So that will become 0. So it will be 0, 0. Then again, V1 theta 1. So again here see V1 theta 1 is this, theta 1 theta 1, V2 theta 1 and theta 2 theta 1. That will be 6, 4, minus 6 and 2. Same thing we have to repeat there. So we will write the same thing there. We will write the same thing. So it will be 6, 4, minus 6, and then we will have 2, then 0 and 0. Then V1 V2. Next will be V1 V2. So how we will get V1 V2? V1 here, V2 here, right? So that is minus 12. So that will be minus 12. So we'll write here minus 12. Similarly, this will be minus 6. Similarly, we will see that K1 matrix and K2 matrix. Already in the previous classes we have discussed V1 theta 1 will belong to, because if we are talking about element 1, that will be between node number 1 and 2. So V1 theta 1 will be only in element 1. Now coming to element number 2, there will be V2 theta 2 and V3 theta 3. Means V2 theta 2 is common in element number 1 also and element number 2 also. So whenever you are writing the elements for V2 theta 2, be careful, because the value will be in element number 1 also and it will be in element number 2 also. Yeah, if you are finding with the relation of V1 theta 1, you are going to find that value in K1. If you are going to find the elements with the relation of V2 theta 2 with respect to V3 theta 3, you are going to get in only element number 2. But the relation between V2 theta 2 with its own relation of V2 theta 2 means what I am talking about. I am talking about V2 T2, this position, theta 2 V2, this position, then again V2 theta 2 and theta 2 T2. These 4 positions will be in element number 1 also and in element number 2 also, because node number 2 is common. Remaining, if node 1 is there, that will only be, you will find this value in only in element number 1, K1. See here, V1 theta 1 is only in 1, right? So there is no issue in copy, just you have to copy paste from here. Now coming to V3 theta 3 is only in element number 3. So whatever the elements you are going to write there, that will be only from element number 2. But coming to V2 theta 2, here also there is V2 theta 2, here also there is V2 theta 2. But V2 theta 2 with respect to V1, see, with respect to V1 and theta 1, there is no V1 theta 1. It means you are going to get in only element number. V2 theta 3, theta 2 with respect to V3 and theta 3 only in element number 2. But whenever we are calculating for V2 theta 2 with respect to its own V2 theta 2, here also V2 theta 2 with respect to this V2 theta 2, see, we will have values in element 1, a stiffness matrix in element 1 also, a stiffness matrix in element 2 also. So for particular elements, be careful and just before writing, verify the values in element 1 also and element 2 also. That's it. Remaining thing we have to copy paste. So here see, till here we have reached. So let us erase this and write the element. So V2 term. Here we have to write V2. So see, in K1 also there is V2 and there is V2, that is 12. And here in element number 2 also V2, that is 12. So here we need to add these two. 12 plus 12, that will become 24, right? So we will write here 24. Similarly, if you will see, that will become minus 6 plus 6, theta 2 V2. See, theta 2 V2 minus 6 and here theta 2 v2 plus 6. 6 plus minus 6, 0, right? So I am going to write it here 0. Similarly, I am going to write other values, minus 12, that will be 6, then again 6, 2, then that will again become 0, then this is 8, minus 6, this will be 2, then we will have 0, 0, minus 12, minus 6, 12, minus 6, and then 0, 0, 6, 2, minus 6, and 4. So we have calculated the global stiffness matrix. Yes, the common is 8 into 10 to the power 5. So we have calculated the global stiffness matrix. So what we do now, the next will be to establish the relation, that is F is equal to K into delta. So before establishing the relation, let us see what are that F2D, F3D. Just we will see that F2D and F3D values that we have taken here. So let me write that F2, yes, these values. Now, if you will see F2D and F3D forces at this point, second node and third node, due to this application of UDL. So UDL is nothing, 12 kilonewton per meter. So if you will see, half of this load will come to node number 2, half of this load will come to node number 3. So this is UDL, we will convert it into point load, means we need to multiply it with the given span. So 12 into 1 will be 12. So directly I can write F2D will be equal to WL by 2. And here it will also be equal to WL by 2. Half of this load, because load will be W into L, W is 12, L is 1. So 12 into 1, 12 by 2, that is equal to 6. So in Newton, we can write it as, directly I am writing here, F2D will be equal to F3D will be equal to 6000 Newton. In Newtons I am writing, because 12,000 divided by 2, 6,000. Now M2D will be equal to M3D, that is due to this load, fixed end moments, you remember, WL square by 12. So this will be equal to, these both will be equal to WL square upon 12. So WL square upon 12, W is 12, L is 1 upon 12. So once you will calculate it, you are going to get 1000 Newton meter. So that is, we have calculated the value of F2D, F3D, M2D, and M3D. This all depends upon the load. If the load intensity will be different, these values will be different. And remember one thing, whatever the load is given, whatever the values are given, we have to take that values in Newton and mm, so that final answers will be easy to calculate, right? So next, we are going to establish the relation F is equal to K into delta. Now K matrix already we have calculated, delta matrix we know, F matrix also we know. So let us write the F matrix, K matrix, and delta matrix, and then we will apply the boundary condition. So F matrix we will have at node number 1, F1 plus F1D. We know this F1D is 0 because there is no load. Later on we will keep in boundary condition F1D value 0. Next, coming to moment, M1 plus M1D. Next, force is F2 plus F2D. Why I am writing these things? So that it will be convenient for you to understand what is the format of this force, right? Yes, if there is no load, F1D value will be 0, M1D value will be 0, because we have calculated only F2D and F3D, because there is no load at node number 1, right? So now next, F1, M1, F2, M2, F3, M3. Right? This is a force vector. So only due to a sequence, to maintain a sequence, I am writing this. Otherwise, first two values, this F1D and M1D is 0. Then into K matrix. K matrix 8 into 10 to the power 5. Now already calculated the K matrix. Then K matrix is going to be 12, 6, minus 12, 6, 0, 0, 6, 4, minus 6, 2, 0, 0. Then we have minus 12, minus 6, 24, 0, minus 12, 6. Then we have 6, 2, 0, 8, minus 6, 2. Then we have 0, 0, minus 12, minus 6, 12, minus 6. And here we have 6, 2, minus 6 and 4. And then we have the displacement matrix. The displacement matrix, we know at node 1, V1 theta 1, node 2, V2 theta 2, node 3, V3 theta 3. That's it. So we have written the F is equal to K into delta. We have established the relation. Now coming to boundary condition, that is very, very important, because by using the boundary condition itself, we are going to remove the things. So boundary condition. Boundary condition. So let us see the boundary conditions. So what are the values? That is going to be 0. So V1 is equal to theta 1 is equal to 0. First thing. Why? Because if you will see the problem, at node number 1, there is a fixed support. Whenever there is a fixed support, the displacements are going to be 0. So at node number 1, displacement is V1 and theta 1. These all two values is going to be 0. Right? Next, boundary condition. Next, we are going to write V2 is also 0. V2 is given 0 vertical displacement, and V3 is also 0. See, V2 and V3, this will not allow any vertical displacements, right? Because here you can see it will not allow this moment in the vertical displacement. Yeah, it will allow in horizontal direction, but not in vertical direction. So V2 also 0, V3 also 0. Yeah, theta 2, theta 3 value will be 0 because it will allow the rotation. Here the slope may be there, but there will be no vertical displacement because this is hinge support. It will not allow you to go down. Just it will allow you to move in x direction or rotation itself. Only two is possible, but here vertical displacement is going to be 0. That's why V2 is also 0, V3 is also 0. Next boundary condition we will see. V3 0, F1D is equal to M1D is equal to 0. Why? Because at this node there is no load, right? If there is no load, there is no F1D term and M1D term, right? Next, F2D, already we have calculated F2D. F2D will be minus 6,000 Newton. Why minus? Because the load is acting downward, so it will also be in downward direction. So minus 6,000. Then we will have M2D, that is also equal to minus 1,000 Newton meter. Already these things we have calculated. F3D is also going to be minus 6,000 because load is acting at third node number 3. Also the load is acting downward only. You can see this is a UDL. So from node 2 to node 3 the load is acting downward. So that value is going to be minus. We will take that as minus. M3D is going to be plus 1,000 Newton meter. Now there will be a question, sir, why we have taken M2D value is minus 1,000 Newton meter and M3D is plus 1,000 Newton meter. So see here, if you talk about this element number 2, if you're talking about this element number 2 from here to here, so this M2D and M3D is nothing. This you can consider as fixed end moments. You can consider this as fixed end moments. If you will consider as fixed end moment, So already we have discussed if it is on the left. So if you will start from B to C, because this is element number 2. So on the left, we will take minus. So for this, it will become minus. And for this, because this is on the right side, C, third node. So for this, it will become plus. So M3D value will be plus and M2D value is going to be minus. That's why I have taken these values. Next, M2 value and M3 value is 0. M2 is equal to M3 is equal to 0. So these are the boundary conditions. So first, what we need to do, we will see these things also. But first, what should we see? We should see the displacement. What displacement are going to be 0? V1 is going to 0. Okay, right. Theta 1 is going to 0. Okay. V2 is going to 0, right? Then V3 is also going to 0. Okay. So once these displacements are 0, so we have to remove the rows as well as columns in the stiffness matrix. So if it is 0, this column is gone. Just remove it. If this is 0, this column is gone. If it is 0, the third is also gone. If it is 0, this corresponding is gone. Now this is first one, right? So first this also gone. Then theta 1 is also gone. V2, remove this. Then theta 2, okay, it is there. Then V3 also. So you can, I will underline the, see, leftover elements 1, 2, 3, 4. This is here left, this is outside. So the reduced matrix is of size 2 by. Okay, so we got this reduced matrix. So from here we have seen we have 2 by 2 matrix. Already we have discussed that we will get the 2 by 2 matrix. So this is the 2 by 2 matrix. Here also M2 and M3 value is going to be 0. So this M2 and M3 value is going to be 0. M2D value is minus 1000. So this value is minus 1000. And M3D is 1000. So this value is 1000. So if you will write the equation from here now, what will be the equation? We can write that equation. Let us write the equation. So we will get this 8 into 10 to the power 5 will be outside. So 8 into 10 to the power 5. To the power 5 into 8 into theta 2, 8 theta 2 plus 2 theta 3 is equal to minus 1000. This is equation number 1. Second equation, again 8 into 10 to the power 5 outside. Then we have 2 theta 2 plus 4 theta 3 will be equal to 1000. This is equation number 2. Now we have two equations, two unknown. Very simple equation, right? From here, we will be able to calculate this theta 2, theta 3 by using calci itself. So we are going to get that theta 2 and theta 3 value as, therefore, we will get theta 2 value. I'm writing that value directly, minus 2.67 into 10 to the power minus 4 radian. And similarly, we will get theta 3 value as 4.46 into 10 to the power minus 4 radian. So we got this theta 2 and theta 3 values. So our problem is almost done now. Half of the problem is solved. Mostly they will ask the question till here itself, but in this question they have asked one more thing, and that is we need to calculate the vertical deflection at the center of the load. So how we will calculate the vertical deflection at the center of the load? In most of the cases they will ask the problem till here itself. So nothing to worry about. Whatever the thing we have studied in bar element, beam element, and continuous beam, the process is going to be same. Nothing is going to change. First we need to identify the nodes, then followed by finding the stiffness matrix, and then followed by finding the global stiffness matrix, followed by establishing the equation F is equal to K into delta, then followed by removing the corresponding columns and rows from that relation by using boundary condition. As the displacement values are 0, the corresponding columns and rows will be removed and we will get the reduced matrix, and then we will find the unknowns from the reduced matrix. So this is all about this type of problem. Only these steps we need to follow. But in this problem, they have asked one additional thing, that is vertical deflection. So let us see how to calculate that vertical deflection. So second part, this is the second part of the question. Part 2, we can say that we need to calculate the vertical deflection. Vertical deflection. Vertical deflection we need to calculate where? At midpoint. At midpoint of distributed load. Distributed load. So from this language, it is very clear that we need to consider only element number 2 in this case, because midpoint of distributed load means what? The distributed load is in element 2, not in element number 1. So let me draw that. If you talk about the nodes, this will be your second number node. This is your third node, right? And there is a UDL over this, having intensity of 12 kilonewton per meter. Okay, so we need to calculate the vertical deflection. Yes, the span also, let me mark this, span 1 meter. So where we need to calculate? We need to calculate at this point, that is at a distance of L by 2, or here we can say 0.5 meter. So at a distance of 0.5 meter from second node or 0.5 meter from third node, because it is at the mid span, right? We need to calculate the vertical deflection. So how we are going to calculate? So let me, this is your global node numbers, right? Global node numbers 2 and 3. Let me take this local node number as 1 and 2, or else we can take 2 and 3, no problem. Just for convenience, I have taken 1 and 2. So we will work out for 1 and 2 only, because we need to calculate for only element number 2. So we understood, okay. Let me take this is as node number 1, this is as node number 2, and I will write it here again. So don't be confused. This node number 2 and 3 that I have marked is global nodes. Global nodes. And I am taking this as 1 and 2, that is local nodes. Now what is global nodes, local nodes? Global node means if I will see the whole problem, the problem in that problem, this part having node number 2 and 3. But since I am analyzing this part separately, so I am considering this as 1 and 2. It's your wish, or else you can go for node number 2 and 3 only. Okay, not a problem. Just to show that the relation means that what we have derived, the shape function, not to change that notations, I am taking this as 1 and 2. Or else if I will change the notation, then I can take 2 or 3 also. You will try, get to understand why I have done this. See, now the V, vertical deflection, can be written as, already we have discussed these things in shape function. This I am using from the shape function of a beam element. V can be written as N1 V1 plus N2 theta 1 plus N3 V2 plus N4 theta 2. This is the formula, right, of a vertical displacement at any point or at any section in the beam. So to maintain this V1 terms like N1 V1, N2 theta 1, N3 V2, V1 V2 terms, see, I am taking this 1 and 2 node, or else if you will take 2, 3, so it will be V2 theta 2, then it will be V3 theta 3. Your wish. It's completely your wish. Whatever you want to take, you can take. What is this N1, N2, N3, N4? We know these all are the shape functions. N1, N2, N3, and N4 are the shape functions. Shape functions. Already we have derived the formula for this N1, N2, N3, N4 also, shape function of a beam element, where I can write here, where N1 value is 1 minus 3x square upon L square plus 2x cube upon L cube. This is 2. N2 value is given as x minus 2x square upon L plus x cube divided by L square. N3 value, we have N3 value 3x square upon L square. The shape function is very, very useful for finding these types of vertical displacements. Basically, for finding vertical displacement, this shape function is very, very useful. You should remember these formulas, at least for beam element, bar element, and x cube upon L square. So we have this N1, N2, N3, and N4 values. Now we will apply the boundary condition. What is that boundary condition? So boundary condition, we know already we have taken this V2 and V3 0, means this V1 and V2 is 0 because there will be no vertical displacement at node number 1 and node number 2. So V1 and V2 value is 0. So V1 is equal to V2 is equal to 0. That is the boundary condition, right? Theta 1 value already we have calculated. Theta 1 value is minus 2.67 into 10 to the power minus 4 radian. Already we have calculated theta 1 value, right? This theta 1 value already calculated in the previous sheet, minus 2.67. Actually, I have converted node 2 into node 1, right? So this will become theta 1 only, right? So theta 1 calculated, as well as we have calculated the theta 2 value also. That theta 2 value is 4.46 into 10 to the power minus 4 radian. So already we have this V1, V2, theta 1, theta 2. See, already we have V1, theta 1, V2, theta 2. These values we have. We have to only find this N1, N2, N3, N4. Once we will get this N1, N2, N3, N4, we will just keep it here and we will get the vertical displacement, right? So let us calculate N1 now. So let me write now the equation. So if we are writing here, see this term, we have N1 V1 term. Since V1 is 0, this whole term will become 0 or not? Since V1 value is 0, this whole term is going to 0 or not? So is there any use of calculating N1? No, that is waste of time. If you want to calculate, you can. But again, if you will multiply anything with 0, it is going to be 0. Again, see, V2 is also 0. So what is that coefficient for V2? Since V2 is 0, so overall this whole element is going to be 0 or not? Right? Obviously it is going to be 0. So there is no need to calculate N3 also. There is no need to calculate N1. Even if you will calculate also, you are going to end up with the value 0 itself. So what is the use of calculating? That is completely waste of time. So only we will calculate this N2 value and N4 value, because we have the value of theta 1 and we have the value of theta 2. So these two terms are non-zero terms. So let us calculate N2 and these two terms. Let us calculate these two, N2 theta 1. So I am going to calculate directly this term N2 theta 1. So let us write N2 theta 1. N2 theta 1 is equal to, now what is N2 now? N2 x minus 2 x square by L. So what is x value now? That is the question. What we will take the x value? See, what is this x value? This is 0.5 meter. We have to keep x in place of x. We have to keep 0.5 meter, because at any section, at a section of x, we can find the vertical displacement. Here x value is nothing, given as at the midpoint. Midpoint means what? Half of this. Half of this means nothing, 0.5 meter, right? So x is 0.5, so we will keep 0.5. So n2 theta 1, so 0.5 minus 2 into 0.5 square upon L. L is 1, right? So 1 plus x cube, 0.5 cube upon L square. 1 square is 1 only, into theta 1. Theta 1 value is, already we have calculated theta 1 value, that is minus 2.67 into 10 to the power minus 4. Once you will calculate this value, you are going to end up with the value minus 3.338 into 10 to the power minus 5. Similarly, we are going to calculate the next term, non-zero term, that is n4 theta 2. So let us write n4 theta 2. N4 is minus x square, so minus 0.5 square upon L, 1 plus x cube, 0.5 cube upon L square, that is 1 square is 1 only, into theta 2, that is 4.46 into 10 to the power minus 4, that is going to, we are going to end up with the value of minus 5.757 into 10 to the power minus 5. So we have these two values. So directly we can write now. Let me take one more slide. V is equal to n1 v1 plus n2 theta 1 plus n3 v2 plus n4 theta 2. This term is going to be already, this term is 0, this term is 0. We have calculated n2 theta 1 and n4 theta 2. So V is equal to these values, already we have these values, minus 3.338 into 10 to the power 5 plus minus 5.757 into 10 to the power minus 5. So we are going to end up with the value of V as minus 0.08913 mm. We are going to get this value. This is the vertical deflection at mid span of the distributed load V. So if you want to represent it, you can represent in element number 2. You can represent it in this form also. This is your element 2. Element 2, that is node number 2, node number 3. Here at the center. Here at the center, that is from here x is equal to 0.5 meter. Center, we have the vertical deflection as V, that value is 0.08913 mm. That's it. You can represent in this form also. So we have calculated the second part of this problem, that is vertical deflection at mid span. If they will ask the vertical deflection at L by 4, L by 3, anything they are going to ask, then you can solve. Just we need to take the value of x as desired. Whatever in the question they will ask, just we will take this x value. That's it. We are going to end up with the required value. So this is all about this problem. We have completed this problem. So we have calculated this in two parts. First part we have calculated is the value of theta 2 and theta 3, and the second part we have calculated the vertical deflection at the mid span of the distributed load. Okay, so our problem is completed now.